Hi everybody, this is Dr. Bricker here with a review for Exam 2. So Exam 2 is covers chapters 23 through 25. So 23 was a circuits chapter, 24 was magnetic fields and forces, and 25 is mostly Faraday's law, induction, a little bit with electromagnetic waves. This spans homeworks 4, 5, and 6, so make sure you finish those or go back and take a look at those. If I were going to study for this, I would definitely go back and look at the homeworks, go back through the PowerPoints if you have time, skim through the chapters. You have all the content videos. There's a lot of information there, I understand. In preparing for the test, I would definitely make like a formula sheet. Pretend like you're in an actual in-person class. I allow you to make your own formula sheet. I would do that, have it nice and organized so you're ready to go with the test. I mean, you're on your own, once it starts. And this test, I'm actually giving you an hour and 40 minutes. A couple people said they didn't have enough time, so I'm adding 10 minutes to this. But if you spend your time trying to Google the problems, you'll run into your own problems because I've made all these problems up from scratch. So make your own formula sheet, be organized. Look at the homework, PowerPoints, things like that, and I think you'll have no problem. Okay, so I just wanted to kind of go through this. There's 10 questions on the test. We've got 3 from Chapter 23, 4 from Chapter 24, and then 3 from Chapter 25. And as we go through this video, I'll give you some hints on what to focus on and maybe what not to pay too much attention to. Okay, so Chapter 23 was the circuits chapter, so you'll definitely have a question about series circuits. So series, you have a battery, so a source of EMF, and you have resistors, maybe something like this. You can take a look back through the circuits lab too if you want to, and you'd have a resistor here, maybe another one here. There could be more. I'm just writing a couple of putting just a couple of resistors. It's series because it's the same current that goes from the battery through this resistor, and all the way back around. So the thing to know is, for a series circuit, the current is the same. And you saw that when you did the lab. So it's the same current. The symbol from current is I. The voltage across this resistor and across this resistor add together to give you the voltage of the battery. So voltage of the battery, this would be V1 plus V2. And if you had another one, it would be plus V3. So when you did the lab, you actually came up with this. The total resistance for this kind of circuit, the equivalent resistance, you can just add them together, and you get the equivalent resistance. Now, if you wanted to figure out the amount of current in this circuit, you can use Ohm's law. So V is equal to I times R. Instead of V, I just use squiggly E. That's what the voltage of the battery is. And then the current would be the EMF of the battery divided by the total resistance of the circuit. So maybe I'll even put like equivalent here just to really emphasize this. And in this way, you could figure out how much current you have. So if this resistor was 20 ohms and this resistor here was 10 ohms, V1 would be twice as big as V2 because Ohm's law, V is equal to IR. If it's the same I, the resistor with the higher resistor value will have a bigger voltage drop. Regardless, they both have to add up to the voltage of the battery. Okay, and you saw that when you did the lab. Okay, very good. So you know how the voltage and the current works, and just in general, here's Ohm's law. So know that information, and then another thing we have is parallel circuits. A parallel circuit looks like this. And you could have more resistors. I'm just putting 2 here. Here's the battery. This could be R1 and R2. So here's the total current coming out of the battery. It's the same thing that goes back into the battery. And some of it goes this way, and some of it goes this way. And this could be I1 and I2. Okay, so for a parallel circuit, it's the voltages that are all the same. So this would be equal to V1, this would be equal to V2. By V1, I mean the voltage that's across this resistor. By V2, I mean the voltage that's across this resistor. So in parallel, the voltages are all the same, but the current adds up. So the total current would be I1 plus I2. And you saw that when you did the actual lab on this. The equivalent resistance in this kind of circuit, you have to add it like this. 1 over R1 plus 1 over R2. Okay, very good. Same thing here. You can figure out the total amount of current from what we did before, and then divide both sides by the equivalent resistance, just like you saw there, to get the total amount of current. Okay, so in parallel, if you keep adding more and more resistors, like R3, R4, R5, the total resistance actually goes down the way that you add them together here. So right now you'd have, say they were both 10. 1 over 10 plus 1 over 10 would be 2 over 10. When you take the reciprocal of that, you would have 10 over 2. Now if you have 3 of them, you'd have 1 over 10 plus 1 over 10 plus 1 over 10 would be 3 over 10. And then when you take the reciprocal, that's even smaller. So the more and more resistors you add in parallel, the smaller the overall resistance. In a sense, you're giving the current more paths to follow, so the overall resistance is less. Okay, so definitely know this information about parallel circuits. Okay, and let me give you another example. If R2 were like 20 ohms and R1 was only 10 ohms, you would get more current going through R1, and you would get less current going through R2. Okay, but you could still figure out the total amount of current. Okay, very good. There will be one complex circuit on the test, so don't be afraid of the word complex. It just means a combination of series and parallel. Let me just give you an example. By the way, through reading through the chapter, you've come across the term simple circuit. There's nothing simple about it. It's just there's one battery and one resistor. There's nothing easy about it. That's just called a simple circuit. Just like this one's called a complex circuit. So here's a few resistors. Current comes out of the battery. You can call this the total current if you want to. Some of it goes this way. You can call these things whatever you want to. I2, we can call this one I3 if we want to, and then they come back together. So the total current, that's the amount that's actually going through R1. This would be I2 plus I3. Now if we wanted to figure out the total current, we could. Now if you think about this, current comes out of here, it splits off, some goes this way, some goes that way. We could take this complex circuit and make it into a slightly easier circuit. So our goal here is to figure out what the total current actually is. So we can replace R2 and R3 with an equivalent resistance. How are we going to do that? These are in parallel, so we can add them like this. And I'm going to call it R23, the equivalent resistance of 2 and 3. This would be like 1 over R2 plus 1 over R3. Okay, so let me just make up some numbers. Let's say this one was 10 ohms. I'll write it over here. R2 is 20 ohms, and R3 is 30 ohms. So I'm just making up some numbers. And you want to get the equivalent resistance for this parallel part. 1 over R23 would be 1 over 20 ohms plus 1 over 30 ohms. And you could do that with your calculator if you want to, or we could use a common denominator, which would be 60. This would be like 3 over 60 ohms plus this one over here would be 2 over 60 ohms, 5 over 60 ohms. It's not my best 5 I've ever written. So 5 over 60 ohms. That's 1 over R23. So then when you flip it over, this would be 60 ohms over 5, which would give you 12 ohms. So you can take this more complicated circuit and make it into something that looks like this. We still have R1. We haven't done anything with that. But now we have this R23 part. So I replaced R2 and R3 with what I'm calling R23. And then this circuit, R1 and R2 are in series with each other. So you just add those together in series. So you'd have the voltage of the battery, whatever that is. So R1, 10 ohms, I have it up here, plus R23, which would be 12 ohms, so this would be 22 ohms. and then the total current would be the voltage of the battery, presuming that we know what that is, divided by 22 ohms. There, you can see it a little bit better. Okay, good. So there'll be a complex circuit, and be aware of what we just did here. We made it into an easier circuit, and from that we could figure out what the total current was. Okay, very good. So that's there's 3 questions from chapter 23, and then we moved into chapter 24, which was the magnetism chapter. And in that chapter we saw some scenarios where you could actually calculate the magnetic field, and then we saw what happens to a charge moving in a magnetic field. So just to refresh your memory, we had the magnetic field due to a loop of wire. The number of loops, mu0 I over 2r. And we can only figure out the magnetic field right in the center of a loop. Now, if this is tightly wound together and there's 1,000 loops or something like that, you've got to put that 1,000 in here for n. Mu0 is just a constant. Make sure you have that written down somewhere. 1.26 to the minus 6th Tesla meters per amp. Let me just verify that it's to the minus 6th. For some reason, I'm doubting myself right now. Yep, minus 6. 1.26 to the minus 6 Tesla meters per amp. That's mu0. So for the loop, you can only figure out the magnetic field right in the center. We had the magnetic field due to a long straight wire, and this was mu0 I over 2 pi r. And r is the distance away from the wire. So if you've got current flowing on a wire, and you want to know the magnetic field, say up here, this would be the distance r. Now, to get the direction of the magnetic field, that's our first right-hand rule. Put your thumb in the direction of the current, and then the magnetic field curls around that. So it's coming out at you everywhere above the wire, and then below the wire, I've got to try to twist my arm around, it's going into the page. Okay, so that's the way to get the direction of the magnetic field. And then here's the formula to get the strength of it. And then we had the magnetic field of a solenoid. Okay, mu0 I, and then n divided by L. And in this case, n is the number of turns, and then L is the length. Okay. And you saw from the homework, the radius of this thing doesn't even matter. So it's something like that has an actual shape like this. And we're looking at the magnetic field inside of a solenoid. Okay, so if you know the current and the turns ratio, you can get the magnetic field strength. Okay, so you'll see you'll see 2 problems dealing with this. Here's a hint. Go back and look at homework 5. Homework number 5. Look at the hammerhead shark problem. I believe it's number 6 from homework 5. It's the 6th one on it. And it's dealing with the shark. And then also from homework 5, we had a long straight wire problem. And it was the second one from homework 5. So homework number 5, and this is the second problem. Okay, and it's something like this. There's a couple of wires, and you wanted to figure out the magnetic field somewhere between them. And this hammerhead shark problem, you were trying to cancel out the magnetic field at the center of a loop. So here's a hint. Go take a look back at these problems. Be familiar with those. Okay. Very good. So those were 2 problems dealing with how to produce magnetic fields. And then we got into what happens to a charged particle moving in an external magnetic field. So remember this, F is equal to Q V B sine of theta. And this theta is the angle between V and B. Okay, so if you've got a charged particle moving in a magnetic field, it's going to experience a force. And this is the way to get the magnitude of it. Many times it's like a proton or electron, it seems like, going in a magnetic field. So don't forget what the fundamental charge is. 1.6 to the minus 19th coulomb. So if it's an electron or a proton, you know the magnitude of the charge. So you'll see some problem dealing with this, using this. Also in the chapter and the lab that you did, or maybe you're doing it right now, the force on a wire. So just to narrow things down, on the test I did not do force on a wire. I did force on just a moving charge. So be familiar with this formula. This is the charge, this is the speed, this is the magnetic field, this is the angle between V and B. I actually made them perpendicular to each other on the test. So theta is 90 degrees, and sine of 90 then is 1. So that makes this actually a little bit easier. So when V and B are perpendicular to each other, this becomes the formula. Okay, and then you also need to know the direction, so you're going to need to use the second right-hand rule. This is from the book. V is the direction of your thumb, B is the magnetic field, and then F is the force. I don't know if you can see that very well. So you've got to line these things up. So put your thumb in the direction of the force, pointer finger in B, and then the force is where your rest of your fingers go. So the force here is always perpendicular to the plane that's made by V and B. Okay, so you've got to line those things up. So we got north, south, east, and west, but now we also have up and down. So don't forget about that. Like, out of the paper, we use this for out of the paper, and then we use this for into the paper. So not only do we have north, south, east, and west, you also have out of the paper, and then this one is into the paper. Okay, so take a look back at that. You'll see a problem like that, but you also have to get the direction. And then we looked at some applications concerning this. So let me narrow it down for you in that regard. We looked at mass spectrometers. So if a charged particle is moving in a magnetic field, it experiences a force. The force is perpendicular to the velocity, so the object's going to, the magnetic force is going to be towards the center of a circle, so it's going to make things go in a circle. So from homework 5, the last 2 questions, if you remember, it looks something like this. We had a charged particle. I don't know if it was positive or negative. Let's just say it's a charged particle, enters a magnetic field, and it goes in a circular path. Hopefully you remember that. Let's, for fun, just say that the magnetic field over here is into the page. So this is the magnetic field, and it's following this kind of path. We could look at really Newton's second law for this one. The net force is ma, but when you're going in a circle, it's a centripetal force along the radius towards the center. And we know from physics 220 that that's equal to v squared over r. Okay, and then what is the force towards the center? Magnetic force q v b. There's a sine theta here, but this is perpendicular the way I have it drawn here, so it would be the sine of 90. One of the v's actually cancels out, this one and this one. So we have mv over r is equal to qv. So if the one on the homework, I think we had to figure out the radius, so just have to do a little bit of algebra here. Over qb would be equal to the radius. So if you know the mass and you know the speed and the charge and the magnetic field, you could figure out the radius of this circle. Okay, so be familiar with that idea. This is actually 2r here, but this is the radius here. Okay, so the one in the test, I give you the radius, I ask you for something else. So you might have to do, this is a great place to start. Mass spectrometer, here's what we have. You might have to do a little bit of algebra, like, for example, if I asked you what the mass was and I gave you everything else. Okay, hopefully you see what I'm saying there. Okay, and then we have chapter 25, which is induction. And I've got 3 problems from that chapter. So this dealt with mostly with Faraday's law. So a changing magnetic field induces an EMF. It actually makes an electric field. But we first saw this with it just in terms of inducing an EMF. So the induced EMF, we had a change in magnetic flux. Okay, so what is magnetic flux? It's the magnetic field strength, cross-sectional area, and then the cosine of the angle between those. So one of those three things have to change. The magnetic field has to change, the area of the loop has to change, or the angle between B and A has to change. So if this is a loop, don't forget that this is how the area vector is defined, perpendicular to the loop. Okay, so if B is this way, this is the angle between B and A. Okay, so when B and A are actually lined up with each other, that's when the flux is the greatest. Okay, so you've got to change one of those things. So if this were a bar magnet over here, hopefully you can see this okay. If the tip of my pen was a bar magnet, north is pointing that way, I could change the magnetic field strength through the loop. How could I do that? Well, I could move it away, move it towards, move it away, move it towards. While that's happening, I'm changing the magnetic flux. I'm inducing an EMF. I could take this loop actually and shrink it and make it bigger, shrink it, make it bigger. That's not very practical, but it's possible. Or you could change the angle between B and A. So for example, you could take this magnet and rotate it this way, that way, this way, that way. Or leave the magnet where it is and rotate the loop. So there's three ways to induce EMF. You've got to change B or A or the cosine of the angle between there. So know that idea. There's a conceptual problem dealing with that. Some other problems, we gave you the loop and you had to just figure out what the induced EMF was. For example, on homework 6, take a look back through homework 6. Problem might read something like, the magnetic field goes from 0 to 0.5 Teslas in a certain amount of time. What's the induced EMF? Well, okay, we could use this formula to figure out the induced EMF. So something's got to change. This is the amount of loops. So if there's only one loop, big N would be 1. So something's got to change. B, A, or the angle between there has to change. So we did several problems where, I don't think we did any where the area actually changed. It was mostly B changing. So N, A, cosine theta, delta B over delta T. Hopefully that rings a bell. So take a look back at those problems where B was changing with time, cosine theta. Now if B and A are lined up with each other, so if this is the area, if this is B here, you can see that the area vectors here, they're lined up with each other. Cosine of 0 is 1. So sometimes this term doesn't really appear there because it's the cosine of 0, which is 1. So it's there, but you don't see it because it's 1. You don't usually write 1 there. Okay. Anyway, take a look back at the changing magnetic field problems inducing an EMF. Okay, and then there's one more, and this is the last one on the test, and it's the last one from chapter 25. We looked at power, intensity, electric field amplitude, that sort of thing. So the power divided by the area is something called the intensity. And don't forget, power is measured in watts, which is a joule per second. So this would be the power, so the watts per square meter, for example. And then this is equal to 1/2, if I can remember this one, speed of light, epsilon naught, electric field part squared, which is also then equal to 1/2 speed of light mu 0, and then the magnetic field part squared. That just comes from this idea that E over B is the speed of light. Okay, so I told you what mu 0 was earlier. Make sure you have that information handy. Don't forget epsilon naught is this thing, 8.85 to the minus 12th coulomb squared per Newton meter squared. Okay, good. So we did some intensity problems with a laser. The area is the cross-sectional area that the wave is going through. So for a laser, the wave doesn't actually spread out in the sense it just goes kind of like this. Now, if you had a transmission tower, like a radio transmitter, the wave spreads out in all different directions. So, for example, if you had something like this, and the wave is spreading out in all different directions, this area turned out to be the area of a sphere, and that would be 4 pi r squared. So again, on homework 6, here's a nice reference problem for you. Go back and take a look at the problem from homework 6, where it was a radio tower transmitting at a certain amount of hertz, and you wanted to figure out the intensity, a distance away. Okay, so there'll be something like that. I didn't put any problem on the test with polarization or anything like that, so you don't have to worry about polarization. The wave problem that's on the test is this sort of problem. Okay, so maybe you can calculate the intensity, and then once you have the intensity, you can get the electric field part. Okay, very good. Okay, so those are the 10 questions. If you have any questions before the test, let me know. Again, I'm giving you 1 hour and 40 for this one, and spring break is coming up after that, so I'm going to make this one available a day earlier than the other one. I know people might have plans, so this will actually be available on Thursday. Okay, again, email me if you have any questions, and I'll talk to you soon. Bye-bye.